So what I've got up on the board there is just from the blue textbook. So if you want to have that open, the same thing as what I've got here on the board, then that is page 324. Okay, so differential calculus or differentiation, okay, is to do with rates of change and gradients. So just in terms of reminding ourselves from last year of what it is, we just need to think when we are finding the derivative of a function, we are finding it may be a value or it may be just an expression that represents the gradient of the function. Okay, so when we're thinking about differential calculus, we need to have in our mind, okay, we're talking about the rate of change of something, okay, or the gradient. Okay, so just in terms of kind of reviewing that concept, you can have a constant rate, okay, which is represented by a straight line. So linear graphs represent constant rates, okay, because your y value is increasing at that same rate all the time as you go from left to right of a graph, okay. Whether it's increasing or decreasing, that rate is constant, okay. We know that if I move to the right 1 unit, it's going to go up a certain amount, okay, each time I do that. All right. When we're talking about average rates, we're talking about finding what the rate would be if I was to perhaps draw a straight line between two values, knowing that it would change any time. So that other graph that we've got there, the parabola, we can see that because it's not a straight line, the rate of change or the gradient is changing constantly. Okay, but if I wanted to know an average rate, then I need to pick 2 points, draw a straight line between them, and find what that gradient is. Okay. But we know that at any particular instant in time, there is a specific rate at which I'm moving. So we know real time, and when we're driving a car, that we're going at a certain speed. Okay, that's an instantaneous speed or an instantaneous rate. Okay, and so we can find instantaneous rates of a curve like that cubic that's there. Okay, and the way we would do that is by drawing a tangent to the curve at that point. Okay, a tangent being a line that just touches a curve in that one spot only. Okay, and so the gradient of the tangent would be the gradient of the curve at the point where it is a tangent to it. Okay, which kind of then leads naturally onto this thinking in terms of if we were given a particular function, we could draw or we could sketch the gradient function of something. Okay, so we could draw we could draw a sketch as to terms of looking at this cubic here in terms of what the gradient is doing. So as we're just sort of looking at this, if we're going from left to right, okay, picking a point, okay, or a couple of points that are close together on this curve, okay, at this section here, then we know it has a positive gradient. I mean, it's almost a straight line. So we can see that it's a positive gradient going up. And then as we get closer to that turning point, it starts to change a little more rapidly. Okay, and that gradient decreases until we get to a point where at the turning point, if we were to draw a tangent, it would be a horizontal line, okay, which would indicate a zero gradient. So it goes from being a positive gradient to a smaller and smaller positive gradient till we get to the turning point where it's zero gradient. And then once we get past that, we can see that if we were to draw a tangent to that curve, it would then start becoming more and more negative. And until we basically got the largest negative gradient in this case would be sort of around about this point here, wherever the point of inflection would be. Okay, and then we can see as we get closer to this turning point here, the negative gradient starts to sort of get like a smaller negative gradient, if you know what I mean, and it gets increasingly positive until we get to the turning point where, again, a tangent here would be a horizontal line, so a zero gradient, and then once we get past that, it's positive again. So we can sketch what the gradient is doing, and we can do that for any given function. It is important to know that the gradient function or derivative could be drawn and found as long as it's continuous, as long as the graph is continuous, okay? So, and that's what it's saying in this point here, is that derivatives can be found at a given point if, first of all, the function is continuous. So we can see here on this particular graph, okay, it suddenly changes. So this this overall graph or function might be represented by what we call a piecewise function. Okay, for part of it, it's a parabola. Okay, it kind of looks that way. It may not be a parabola, but it's kind of got that look about it. And then at this point of -1, it suddenly changes to a linear graph. Okay, so it's composed of kind of two separate functions to come into one. But as a result of that, at this point here, it is discontinuous. Okay, at that point, you could not find the derivative. Okay, you can find the derivative at all the other points on the graph, but just not here. So derivatives can be found when the function is continuous and when, as long as it's smooth as well. Okay, so when we're talking about continuous, we're making sure there's no gaps in the graph. Okay, smooth, we're looking to see, are there any sharp points? Okay, so something like this. Okay, is an example of not a smooth function. Okay, it is a function, but it's just not a smooth function. And so at that point in particular, the gradient doesn't exist, and so you couldn't find the derivative either. Okay, so they're kind of important to note. Whereas we can see here with this cubic type of graph, it is both smooth and continuous, even though it sort of changes the way the curve goes. Okay, so in terms of drawing or sketching gradient functions, if you have a straight line function, then we can find an actual value to draw the gradient function. So here we can see, because we have particular values here of an x coordinate here and a y coordinate, we can find what the gradient is just using rise over run. Okay, being a straight line, it's a continuous, constant gradient. Okay, and we would represent a constant gradient by a horizontal line, meaning it's the same all the time, right? So we look here and we see our rise is 1 and our run is 2, so it has a gradient of 1/2. So if I wanted to draw the derivative function or the gradient function of that, I just need to draw a horizontal line as it's shown here and passing through a y value of 1/2. Okay, because that's saying, all right, our derivative function, which we're sort of using this notation of f dash of x, okay, representing the derivative, okay, and it's just a horizontal line through y equals 1/2. Okay. If we were to look at a quadratic function, okay, we can't be super specific about what the actual graph would look like, but we can find there is some specifics that we can put down. Okay, and that is where we know the gradient is equal to 0. Okay, as we saw before, wherever you have a turning point, that's where a tangent would be horizontal, and so that corresponds to a 0 gradient. And so by looking at any quadratic or any kind of curve where you know there's a turning point, they are key points that you're going to identify as having a 0 gradient. So we can see here at x equals 1, then there is a 0 gradient. Okay, and so drawing the graph then of the derivative function, we know that it's actually going to pass through the x-axis at that point of x equals 1. Other than that, it's not, we can't kind of be too clear about what it looks like in terms of the steepness of the curve. Okay, all we know is that to the left of that x value of 1, it's got a negative gradient. Okay, so the line we would draw would be below the x-axis. After that, we can see that it's a positive gradient, and so it's going to be above the x-axis. And so it's just drawn in that way. Okay, the actual steepness of that line, it doesn't matter. Okay, we just, as long as we've got it clear as to where it's negative, where it's positive, and where it's equal to 0, okay, that's the important thing. Okay, so yeah, if we remember, gradient function or derivative of a linear curve will be a horizontal line. For a quadratic, it will be just a linear graph, could be positive or could be negative slope, depending on whether it's a right way up parabola or an upside down. For cubic functions, again, first step is to find where our gradient is going to be equal to 0. And so we can see here, we've got our turning point at -3, so we're going to have a 0 gradient there. We're going to have a 0 gradient at x equals 1 as well. So those 2 points is where the gradient function is going to be passing through the x-axis. Okay, and then we just need to look and think, all right, to the left of -3, it's a positive gradient, and so the curve of our gradient function has to be above the x-axis because that's where it's positive. It's positive again after x equals 1, and so again that's above the x-axis. But we can see that between -3 and 1 it's a negative gradient, and so that's shown by drawing this curve under the x-axis. Okay, so not terribly complicated, you're just identifying those key points and seeing where it's positive and negative. Okay, so if we just have a look, excuse me, at this example 4 that's on there, it's just got, for the function shown, state the domain of the gradient function. In other words, we just need to see where the gradient function will be defined. Remember, it will be defined wherever it's smooth and continuous. So you're looking to see, are there any points where it is not smooth and not continuous, and that's where it will be undefined. So we can see here that at x equals -1, there's a break in the graph, and so it's discontinuous. So we know the gradient function is not defined at -1, and it's also not going to be defined at this value of x of 2 because it's got this sharp point. So at that point it's not smooth. And so you can show that what the domain would be as it's got here, okay, for all real numbers except, and then so you got that backslash meaning except at, and then inside the braces you can just identify those x values, -1 and +2. Okay, so that's quite a convenient way of just identifying what that domain is. All right, so any questions about that? That's sort of remembering that, okay? So what we'll do, if you want, just go through just a few of those questions. You don't have to do them all necessarily. From question 1, okay, which is on linear. Question 2 is the quadratics. and so on. So you can just keep work through that exercise 7A. For starters, pick and choose as you want. So you can do that for a little bit, and then we'll move forward onto reminding ourselves about limits and differentiation from first principles. So you can work on 7A for a while.